Helen, I don't know if you want to say a few words before I introduce Anthony.
Thanks a lot, Maria. Anthony, it's nice to meet you. I didn't speak out, and I guess things went really well. Thanks a lot for joining us, and this is our distinguished webinar, and we're going to record this and post online as well.
Cool.
And thank you for joining us. And Maria, it's all yours.
Yeah, thanks for the invitation.
Yes, 1 second. I'm having some technical difficulties on my side. 1 second. Yes, so it is our sincere pleasure to have Anthony Rowe with us. He is Daniel and Karon Walker I have no chance of pronouncing that. Siewiorek. Professor in the ECE department at Carnegie Mellon. And Anthony has been doing absolutely incredible work in cyber-physical systems and the IoT. His past work has led to dozens of hardware and software systems deployed in industry, 5 Best Paper Awards, and several widely adopted open source research platforms. And we are absolutely delighted to hear what he has been doing lately.
Cool. Thanks, Maria, for the introduction. Yeah, so today I'm going to be talking a bit about sort of spatial computing in the spatial web. But maybe before I get into that, I wanted to talk a little bit about my background. Okay, so just a quick 2021 check. Slides are working. Okay, excellent. So I'm Anthony Rowe. I'm from the Electrical and Computer Engineering Department at CMU, and my research background is in embedded sensing systems. And so I've done my lab's done a lot of work on sort of hardware building, real-time operating system design, and scheduling. This is like an example of a little sensor board that we built. These are some wireless communication base stations that we've deployed around campus, and then sort of looking at the combination of embedded systems and wireless communication, my group really got into indoor localization. And we started to do work on, for example, safety worker tracking and just generally tracking and sensing across sort of large facilities. And that eventually led to my interest now in sort of mixed reality systems as a way of combining digital and physical and programming them together. And so today I'm going to be talking about some of our latest work that we're doing on spatial web. The other thing that I spend a good amount of my time working on is I'm the director of this CONIX Research Center, which is one of these large semiconductor research corporation sponsored groups. And the CONIX Center is specifically on looking towards the future of distributed computing. And in fact, all of this work on sort of spatial web, spatial computing, whatever you want to call it, is one sort of slice of the work that we actually do within the CONIX Research Center. And this is actually a collaboration with a whole bunch of extremely talented PIs across a bunch of different universities. So some of the stuff that you're going to see in my talk today is actually work that those labs are doing in collaboration with our lab and vice versa. And I'll try to highlight, who's doing what. So to get started, I just to make sure we're all on the same page. I know some of you are probably familiar with mixed reality. Some of you may not be. The idea behind mixed reality is really looking at how to merge digital content in a realistic way with the physical world. And this can happen in a bunch of different forms. This example here on the left is kind of an IKEA demo app where you can put mock-up furniture in your space with being able to look through your tablet as if it's a live window into the environment, all the way to like wearing headsets like the Microsoft HoloLens. And there's a bunch of kind of terminology that people mix up and interchange. And just for the purpose of this talk, I want to make sure we're on the same page. So virtual reality is where you're completely blocked in with goggles, or you're on a computer going through sort of like a 3D game world. Augmented reality, actually, by the technical definition, is really more just a heads-up display where you can have text that's on the screen in front of you that's not necessarily linked with the environment. And then mixed reality is where that augmented reality display actually merges with the physical environment and reacts to it. So you can kind of see on the left here, you could have a heads-up display with some stats about cycling. On the right here, you see that digital content is really linked into this construction application. And then XR is just experience reality. That's kind of the catch-all that people use for everything now. So if you don't want to specify exactly what it is, you just say, oh, it's XR. Just a quick demo. I actually like, this is from Leap Motion, the North Star project. This is actually an open source AR headset, but this gives you a sense of what we mean by mixed reality. You can see that you have graphical overlay that's linked with the physical environment. It's reacting to the user, and it basically becomes sort of this seamless sci-fi holographic type technology. And it turns out that this has been around for quite some time. So just a little bit of the sort of milestones and road marks along the way. So starting as early as 1968, Ivan Sutherland developed one of the first AR systems. This was largely done. These are, I think, an ultrasonic head tracking system. They had a lot of analog compute that was doing kind of graphical overlay in real time. But back in 1968, completely insane. And of course, Ivan Sutherland went on to basically, start the field of computer graphics to make his vision come to life. Then a little bit later, so kind of in the 80s, people started to work on 3D point clouds. This was starting to look at some of that spatial information. 1984, of course, we had the first Terminator, which was one of the first movie depictions of mixed reality. Some people had talked about it in sci-fi, where you actually had kind of semantic overlay mapped with the environment, as well as a little bit of a HUD in the environment. Then you kind of move into the 90s. So 1990s when Boeing, some researchers at Boeing coined the term augmented reality. In 1992 is when we had really the research community started to blossom around. It was where some of the first mixed reality conferences happened. There's a famous Milgram paper on kind of the continuum of reality that talked about programming virtual and digital. Then towards the end of the 90s, some of the robotics community started to work on sort of real-time simultaneous localization and mapping. Early sort of 2000s to 2010-ish, you started to see mobile AR emerge with new sensors that were higher fidelity. In 2016 is when the first Microsoft HoloLens came out. So that was really the first sort of commercially available AR sort of MR headset. Then in 2017, we had a pretty pivotal moment, which is where Apple and Google released mobile mixed reality kits that really sort of democratized a lot of this technology and got it into the hands of folks that normally wouldn't be interested and or sort of capable of going through that whole previous timeline and stack. And then since 2018, we've had sort of an explosion of companies building software and hardware infrastructure around the mixed reality space. And then, of course, just a couple of weeks ago, it feels like this notion of metaverse really went mainstream with Facebook saying that they're now going to be investing, $10 million a year into the space, changing the name of the company. And that sort of leads you to sort of step back and say, is this hype or is there substance? And as electrical engineers and computer scientists, what are the challenges and potential here for us? And I would argue that if you look at some of the applications that are available that could be made possible with mixed reality, they're pretty compelling. So a lot of people have looked at, for example, digital teleportation. So in this scene, you see a mixture of people wearing augmented reality headsets in a space where you've got digital avatars of people where they're communicating fluently. And I think the pandemic brought this to the forefront. You also have this notion of being able to explore remote 3D spaces and help people with remote expertise. So here's kind of an example of somebody who's scanning a factory and then maybe getting assistance from a remote operator. I think there's lots of arts and entertainment examples. You see examples in construction and maintenance. One thing that I've been working on most recently is looking at mixed reality in factories and industrial plants. And here, this is actually an example of projection-based mixed reality. So having projectors that project on surfaces so people don't even have to wear headsets to help basically understand operations of a machine. And here you've got a system that could be sensing a human while they're interacting with the machine with the overlays that are very, very transparent. Medical is obviously a big field, and I know something close to home, especially at Duke, being able to, for example, overlay real-time 3D content into the body, smart cities. So this list goes on and on and on. One area that really shouldn't be overlooked is the defense sector. So one of my predictions is that mixed reality, like many technologies, like GPS, for example, will blossom first in defense and then eventually sort of trickle down into more commodity systems. And the idea in defense systems, what they really care about is you've got all of these different agents and entities that are out in the environment collecting data. They want to fuse it together in a common digital fabric and be able to basically convert all of that raw data into information for people on the field. And then they want to basically prune that information and make it actionable. So they call this sort of enhancing situational awareness. And we're already seeing one gigantic example of this, which is the IVAS program, where the Army is using HoloLens 2 to basically augment soldiers' helmets with this technology. But you're actually also seeing a pretty significant uptick in DoD investment around the mixed reality space. So I talked about spatial computing at the beginning. And so what I mean by spatial computing is really sort of the connection between mixed reality and sensors. And if you look at kind of major platform transitions that have happened in computer systems over the past, we had mainframes, we had home computers, internet, smartphone. I see XR as almost a natural evolution of some of that. So where you take sensors, IoT, which are basically doing physical to digital at the bottom, and this is something that I spent, the majority of my career working on. And then you think that mixed reality is sort of the dual of that, right? It's taking digital and now overlaying it onto physical. And this all is starting to culminate in this common vision that, Facebook calls the metaverse. Other people are actually calling it AR cloud. Some people call it digital twins, although digital twin might have a specific sort of sub-meaning within this, or spatial web, where you have a common view into an environment and you have an overlay of a whole bunch of different applications that are basically working together with multiple users in a common space. And so the reason spatial web is kind of a word that people use to describe that is it actually does have some common properties with the web. And maybe it's worth pointing out a little bit of where that comes from to sort of set the stage for the rest of the work and the talk. So if we look at the current web, you typically have something where you have content, you've got platforms, you've got interpreters, which are web browsers. And these platforms obviously have different capabilities and display technologies. And depending on the platform and the context, the goal of a browser or an interpreter is to render the content in a way that makes sense for your current platform / state. So if you look at this in the context of spatial web, you've got content again, and maybe it is HTML, maybe it's something else, but you also have the physical world. You have platforms as well. Some of these are familiar, the older platforms, some of them are new, like headsets or projection AR. Again, you also have interpreters. And in fact, the main interpreters in the mixed reality space are coming from the same folks that create web browsers that we're used to, with a couple of new players, like Oculus, for example, has a web browser. And what really changes here is the way that you see this information and interact with it is significantly different than just sort of clicks on a web page. So a couple of examples of those. So if I go to a spatial web website in a regular browser, so this is a screenshot of Firefox, I might see a scene that's a 3D environment like this, where I see a background, I see some content. I have links that I can click on to go between pages. If I open that same website on an Oculus Quest 2, it renders in a more immersive version of that, where I can move my head around. Big difference now is I have hands, I have controllers, so that's great. But the interesting thing happens here is if I go to something like a classic AR headset or MR headset like HoloLens 2, I now have that same content, but it's actually anchored into the real world. So here I see, that same thing. I have the same links. I can still click on them. Now I'm just using my hand and gestures. That same scene could also be projected in mobile AR. So here's kind of an example of an iPad that's registered and localized in that same environment that's showing sort of that same content. So you have this ability to write applications that can run across platforms, but are also linked to a physical environment. And I think what this leads to, which is kind of interesting from my perspective. So I'm relatively new to the mixed reality, augmented reality game. I think of it in terms of a playground to explore systems concepts that are closer to my background in embedded systems. And what we're really seeing is that this is giving us this great opportunity for a paradigm shift in edge computing. And if we look at where we are with edge computing today, we've gotten really good at building out sort of cloud-based services that do data management, machine learning, all of that good stuff, Kubernetes for managing compute that's running across the cloud. We've got these highly capable edge devices that are emerging with really cool displays and sensors and actuators. But for the most part, our design paradigm is still very much up and down through the stack, right? These edge devices push data to the cloud and vice versa. When you have situations like what happens in mixed reality, where latency dynamics start to become an important factor, this paradigm of writing software and developing systems really breaks down. So if we look more towards next generation systems, you need a lot more of this sort of back and forth that allows this to happen and scale. You need to be able to figure out where to place compute in environments, where sensor data should be collected, how it should be backed up, maintained. How do you actually program this? And one interesting thing, if we look at sort of the mixed reality space, is it very much started from a device-centric, headset-centric model with early HoloLens systems. The models that people were using for compute and computation eventually got too large to be run locally. So of course we pushed on GPUs in the cloud. And then now, because of latency reasons, it's kind of going back and forth. And I saw the beginning of a great talk that Maria was giving that was talking about exactly this problem of how do we do this partitioning and mapping of compute across these mixed reality systems. So again, from a computer systems perspective, from a EE and CS perspective, lots of sort of interesting problems here. The other question you might ask is, we literally saw this vision start in the late 60s. So why now? And I think one thing that we're seeing now that's a little bit different is ubiquitous localization and really good 3D sensors that can understand the environment. So this is an example of Apple's AR kit doing visual inertial odometry to track a space. You can see sort of the feature points being tracked, but it allows us to anchor virtual content into the world like this. This is an example of the new depth camera that's in a HoloLens that's able to give you a great 3D mesh of the world. We've got Apple now supporting time of flight ranging radios like the U1 chipset that are in phones. So a lot of these core technologies for mixed reality are really becoming much more accessible, much more lower power, much more commoditized. You're also starting to see lots of work on displays. This is kind of an early research prototype of a contact lens with a single LED pixel in it. We've seen, Quest, we've seen all of these different headsets that have come out. We even have, speculations about Apple releasing a headset soon, and then tons of startups in the space of really making all of this technology dissolve into the background. So I think from the perspective of technology going in cycles, we're now at a point where at least the supporting components are there to really make mixed reality happen. So from an XR perspective, there's lots of challenges that have been rapidly improving. Things like registration, localization with pose. This has been done primarily with computer vision, but also with other types of sensing modalities. There's a lot of people that have been working on scene understanding, and of course, deep learning has played a big role here. There's tons of people that have been working on platforms and hardware, so display technologies, controllers, wearables, and sensors. So all the way from sort of the machine learning algorithmic side of the world down to the hardware side, lots of work. Good progress has been made. It's a little bit different than sort of the area that my group and that CONIX in general has been focusing on. So I want to look a little bit more at what we would consider the spatial web challenges. And this comes from sort of collaborative mixed reality and mixed reality systems where you have components that are out in the wild that could be running on untrusted platforms. Here, I think we have more challenges around how do you program the system? How do you host applications? How do you make real-time interaction and sharing of data with low latency possible? How do you deal with real-time mapping and localization in the real world outside of just motion capture environments? And then there's this whole sort of line of work around reality capture and sort of scene understanding, which I think we're just getting to the tip of the iceberg in. So I want to highlight a couple of interesting projects from sort of my group and CONIX in general, and a couple of these different categories. So the first one is really around this idea of what should the software platform look like for building out these types of systems, where you've got programming, real-time interaction. And we've been developing something which we call ARENA, which stands for the Augmented Reality Edge Networking Architecture. And it's basically a platform to simplify building these multi-user wide area mixed reality applications. And so our goal is really to try to make, distributed mixed reality programming as accessible. We used to say as easy as the web, but anybody who does web programming knows it's not actually easy. So accessible as web programming. And it involves a whole bunch of different components, location-based content discovery, obviously being cross-platform, and really trying to push towards this ability to say, I want content in the world to stitch together nicely and work across a bunch of different devices. So I want to show sort of conceptually what the architecture looks like. Then we can dive into a little bit more details and then sort of pop back out and see some examples of what you can really do with it. So what first happens is when you arrive at a location, you need to do a geographic lookup to find content. So we have this thing we call the atlas. It turns out there's a bunch of companies that are working on spatial anchors and different ways to do this. But what happens is you eventually find a pointer to something that we call a realm, which is basically a compute server infrastructure that can feed you some content. So it could give you available scenes, which would be sort of views into the environment, different applications that are potentially running. But most importantly, it connects you with that compute infrastructure. So this would be, in most people's terminology, an edge device that's hosting applications. You might then have a couple of users that are in the space that are wearing headsets. And what the arena does is it takes the users and this compute infrastructure and it places it on a publish subscribe infrastructure. And once you connect to that scene, the publish subscribe infrastructure has the ability to launch a set of applications. And I'll get a little bit more detail of what this runtime looks like later. But these applications launch on the edge device. There's also a component that runs on the client side. And when you're in this realm and you load a scene, we have this abstraction, which is basically very similar to a 3D graphics scene graph, where you have all of the different elements in a scene that represent geometries and such, but it's also sort of mixed up with almost like a Unix notion of /proc/dev, where you have also hardware components and programs that are exposed. And so if, for example, this program decides, hey, I want to draw some content, it basically sends out a message, draw content, where all of the agents that are connected to it receive this message. They see that message in a sort of a standard format that allows them to load the correct file at the correct position based on their context. So you see it draw an object here. That object then appears sort of in the geometry branch of this publish subscribe tree. And then if a user decides, okay, I want to click on this object, that's this user's program now generating a message that goes back to the application over the pub sub bus. You can see that that user input shows up again as an entity in this publish subscribe tree to give the program the IO that it needs coming from the different users. And one thing that I'm not going to go into a huge amount of detail here, you'll see a little bit of it later, is that this whole scene graph is access controlled, right? So when you walk into a space, you can actually hand out JWT style tokens. So basically ACL style tokens that different users, based on their sort of role within the system, can access different parts of the system. So not everybody can manipulate everything. Some people are just can observe, some people can interact, and we have a lot of fine granularity around how that happens. So one of like the fun things under the hood that one of the thrusts that CONIX works on is, what does that whole security model actually look like for these mixed reality systems? So anyway, that program received a click, it got an update event, it updates the graphics, you see like a circle appear that lights up over here. And then one of the fun things that can happen now is I could launch a totally different program that could launch anywhere in the system. And what happens then is that program can also send out commands to basically render graphics, create a new object, and everybody sees it. And so we call this a sort of a network transparent runtime. It means that any program running anywhere can basically create these interactive objects. But of course, there's a timing and a performance penalty depending on where they're launched within the system and within the network. So I can show a little bit of an example of what this looks like through a demonstration video. So here, I'm going to be showing pass-through augmented reality. And the idea, this is basically showing you in the upper right, there's a, turn on the pointer again. The upper right, this is a screen capture of this iPad. There's an optical marker in the floor, which is how the system is figuring out the origin of the scene that it's in. But the first thing that happens is you launch a web browser, and I don't know if you quickly saw the Mozilla thing come up. It's finding scenes that are nearby, the user's clicking on a scene, and then they go into AR mode and they quickly get relocalized. And so when they're walking around in this environment, so I'm going to pause for a second here, you can actually see that in the AR world, other users that are in the space show up exactly where they are, right? So this is, again, using that publish subscribe infrastructure that's sort of network transparent and naturally synchronized. So every user actually is a live entity in that scene. So you can see a person moving around. And then there's going to be an example here where this dot on the floor is actually an application. It's a navigation application where if the user clicks on it, it launches it and it says, okay, here's a path that you can take. So that's one program that's running in the system. You walk through this space. This is another program that's actually linked to the lighting infrastructure in the environment. So this person has access to be able to actually control sort of IoT devices. You can configure lights, turn lights on and off. And again, I'll show some of what these programs look like. It turns out they're actually very simple Python programs. Here, you'll see an example of a program actually launching out of a wireless Raspberry Pi. And of course, it just dramatically appears because it's AR, so why not? But the idea is that this is running on the Pi. It's, again, a tic-tac-toe game, fully collaborative. So that just happens for free based on sort of the architecture of having this network transparency. And you can see that it even is basically reacting to the 3D contents of the environment. So like the table, actually, you'll see when the game progresses, sort of blocks fall off the table. And then you can see examples where it relocalizes, again, another navigation application. So you get the idea. So this is sort of the mobile AR perspective, but that same scene would actually work as well with a headset, HoloLens, and you'll see some examples of that. So to dive a little bit deeper into the architecture that makes this happen, the first component is really that Atlas geospatial lookup. And actually, it turns out that there's a bunch of open source initiatives out there already that are looking at hyper scale distributed content discovery. I think it's a really interesting area to think about. Also in terms of management and curtailing, like, do we really want ICANN for spatial web, or do we want something different, better? How do you actually do sort of content filtering, all of that good stuff? We have a very simple example that basically just gets you data that people post locally, connects you to a Realm environment. And then in the Realm, you have the publish subscribe infrastructure, which we use a modified version of MQTT, but you could use anything else. We also have kind of a REST backend, and you have a number of sort of services that run that nominally are at the edge computer, but actually could be running anywhere because of the way the architecture is made. And this is where we do things like access control. We serve static content. We have a persistence database that kind of stores and tracks the state of a scene while it's running. You then have a bunch of viewers that connect. So this viewer stack is actually built on web technologies. So we use WebXR, we use 3.js and A-Frame, which are all sort of web-based technologies that allow you to have that cross-platform interaction within the arena. And then we have this runtime, which actually hosts and executes programs. And I'll talk a little bit more about that later. But those headset devices are then what basically displays the scene. And we have a bunch of other devices in the environment that are these headless server devices. So if you have robotic systems or IoT devices or anything with intelligence that you want to pop out a mixed reality interface, those operate in this headless mode. And the reason there's really a distinction here is largely because of how we manage access control for devices versus people is a little bit different. So maybe an example to make this a little bit more concrete. This is whoops. I was hoping I could pause this. Can I not pause it? Maybe I have to actually do this the old-fashioned way. Click on the button. Okay, so here you're seeing two web browsers, top and bottom. They're both open in the same scene in VR. On the right side here is a terminal that's showing you an example of a Python program that's running on a Linux machine. And this is a simple program that basically draws, I think, a couple of green boxes. And so if you actually run this program, this is a very dev-centric thing. The first thing it asks you to do is authenticate. This is now pulling down a token using OAuth for my account, giving this program, my user privilege access. But you can see it's basically painting objects into the scene, and you see them showing up in sync across two browsers. And actually, if you move around in the scene, you can in fact see the other user also watching these boxes. And when it downloaded that token, you can kind of see an example of what it looks like. This is a JWT access token that gives you access to different parts of the pub subtree. So this is probably too detailed for this type of talk, but you can kind of look through our interface to see what permissions you have to doing different manipulations. Most importantly, in the bottom right, it's now going to run a different program, which basically gets overlaid into this same scene. So this is really showing the ability to have a bunch of these programs launch and interactively merge together into a single view. And don't forget that this is, of course, also in augmented reality. So this is that same program that's running in AR, drawing boxes across that same scene. And if this is anchored to a particular part of the world, then this content is actually registered and linked into the right space. So sort of another example of this is showing a scene where you have two users. So in the upper view here, you've got one augmented reality user, and the bottom you have another augmented reality user. The right side is going to show virtual reality, and you'll actually see users interacting and basically dropping down components into the environment and sort of authoring and staging a physical space. And interestingly enough, this is like a very early version of this, but we have sort of prototype user interfaces that are used to do this that are actually also Arena programs. So we're building out the sort of the operating system components, if you will, in the same infrastructure that all kind of runs together. But this basically shows you that, because of the implicit networking, you get this in transparent execution of programs, you get this richly sort of interactive space for free where you can sort of develop and build out content. So the sort of next question, I think, for many, especially the CS-minded folks in the audience, would be, well, what does the spatial computing runtime look like? If we have this vision from earlier where we've got cloud middle edge and we know that we have different timing penalties associated with it, what does the programming model really look like here? And our hypothesis is really that this needs to be built around something with distribution, security, and timeliness as kind of first order primitives. And one abstraction that the CONIX Center has really been exploring and looking at is this notion of nano processes. And this is actually work that Dan Stefan and Gabe Parmer from George Washington University and UCSD have been taking a lead on. But the idea here is that you have a lightweight computation abstraction where you have an execution context. So this is basically a program that is able to run. You have a protection context. So the idea is that this program, this thread, is very lightweight, but also completely sandboxed, that has explicit interdependencies. So it has kind of a narrow waist of IO that can come in and out of it. And it's built in a context where you have a monitoring system that can kind of instantiate, that can look at giving it networking access, storage, IO, but through a very controlled set of interfaces. And one of our sort of big philosophical pushes has been for focusing first and foremost on security. So making sure that these things are heavily sandboxed, they're memory limited, you can control all access in and out of IO. And it turns out one place where this has already been happening for quite some time is in the web, in the world of WebAssembly. So WebAssembly is kind of this intermediate runtime language and execution environment where you can take programs that are written in C, Go, Rust, compile them into this assembly intermediate format, and then launch them either interpreted in a WebAssembly runtime, or you can do ahead of time compilation. So you can take that intermediate language and compile it into raw assembly for something like an embedded platform, where you can still maintain some of the provable properties. In fact, hopefully all of the provable properties about memory access coming from the original WebAssembly program. And the interesting thing is that this was built primarily for the web, hence the name WebAssembly, but that it's being adopted significantly actually outside of the browser. It's kind of like a, I don't know, almost serverless, but with state execution environment. And so we're seeing, you know, people using it in IoT. We're seeing people use it for content delivery networks, smart contracts, cryptocurrency. In fact, even some of the sandboxing protection work in Firefox, which has come out of the CONIX Center, is now using WebAssembly to help improve access to libraries. So I don't know that spatial WebAssembly is necessarily the answer, but we certainly do believe that there's a need for a, you know, very lightweight, stateful, intermediate cross-platform execution environment, which doesn't really exist at the level that we're talking about. We have things like virtual machines and containers, but they're very, very heavyweight for a lot of the type of computation that you're going to see in the IoT and the embedded world. And if you look at kind of the natural progression of where embedded software has gone over the last couple of years, I mean, we started off with very specialized systems where you have real-time operating systems, domain-specific hardware, certification, expensive, like, you know, paying crazy amounts of money for just a couple thousand lines of code, to something where you start to see, okay, well, maybe we want some third-party integration into systems. You've got an infotainment system in your car, to the point where some of these systems start to become much more commoditized. And now, you know, maybe you're not even doing certification anymore, and you're opening yourself up to the internet, where really what you want is security, isolation, lightweight, predictable runtimes. And again, we think that this is a great place where nano processes in specific, but WebAssembly as a particular example, could play a critical role in making that happen. So one of the big thrusts that we've been doing around this is this notion of a nano process runtime supervisor. And maybe the way to think about this is it's almost like a Kubernetes orchestration layer, but for the edge. And there are a lot of people that are actually trying to just take Kubernetes and run it on the edge. There's definitely some, there's some drawbacks to that and some challenges, but we've been sort of building out this notion where you can monitor resources when they connect in, you can dispatch code to execute on them. And one big difference between what we're doing and what people have done more traditionally is we look at the interconnect. We actually look at the network, and we use the network as a bit of a roadmap for how we do this partitioning and mapping. And then because we're using these lightweight nano processes, we can also migrate components at runtime to react to dynamics in the system. And one really cool feature that we've built out within CONIX around WebAssembly is we can actually do a live hot context swap across machines. So we can have a program that's running on one computer, actually context swap over to another computer, and it basically believes it's almost like a context swap on a standard operating system, which is, I think, a pretty interesting knob given a highly dynamic environment. So what we've also been doing around the arena is really scaling out the infrastructure. So we have the ability to have these realms that are federated across each other. And through the CONIX Research Center, we've actually had all of the different universities that are part of it launching arena servers. And then, of course, as we're building this out, the pandemic hits. And one thing that we very quickly said was, hey, Zoom, as great as it is, it's keeping the world going. But in terms of engagement and fidelity, it still kind of sucks. Like, we should not be stuck in Hollywood Squares style video conferencing. So we added a couple of extensions to our system. We connected in the ability to do audio and video streaming. We added things like a chat controller. So this is sort of on the arena front end that allows us to kind of in a browser video game style, go around like a max headroom cube and talk to each other. It's spatial audio, so the sound sounds like it's coming from the right direction. You've got video. We have a whole bunch of different bells and whistles. And so one kind of fun example, so this is a project that Paulo Tabueda at UCLA works on. He's a control theory expert, does awesome work. You should definitely check out everything that his lab is doing. But here they put together this example of a drone, which you can see flying in their lab, and it has its digital twin that's flying in the arena. And we're like, okay, that's pretty cool. But in the actual day when they demoed it, they built this interactive multi-user environment where everybody could connect. We had live feeds of his lab kind of pasted up in the environment where you could ask questions, you could point at things, you could move off to the side and chit chat because it's spatial audio. So it's kind of like that cocktail effect. You could look at his posters. It was this just incredible, awesome sort of immersive experience that really actually made you feel like you were there. You got a sense of it. And I actually felt bad because they had some very cool control theory stuff that they were talking about that I think got overshadowed by just the presence of the demonstration. But it really shows the power of kind of where some of this mixed reality technology is going. Here's kind of another just sort of simple example of a robotic system. This was an undergrad project that they worked on where they were able to sort of visualize and show what the robot was seeing in real time, again, just with simple optical markers and an iPad. So really cool to kind of see what's so easily capable. So now I want to kind of switch gears and talk a little bit about one of the big challenges in these systems, which is really the real-time mapping and the localization. And that's something that, you know, the first couple of years at the CONIX Research Center, we focused on heavily. And we kind of saw that at least in the realm of range-based systems, so there's also visual relocalization, all those types of things, you really have this spectrum of like fixed infrastructure on one side to zero infrastructure on the other side. And so with fixed infrastructure, what I mean is you have beacons, you know where they are, you've got a mobile device or a headset, you're in an environment, you're pre-mapped, you're trying to localize yourself. This is still kind of hard for a lot of systems to actually do effectively, and there's still bottlenecks. As you move more towards zero infrastructure, you can think about things like being able to automatically map the location of the beacons as you move through the space. And then finally, you move towards kind of this zero infrastructure world where maybe if we can just track the position and get sort of intermittent periodic ranges between devices, can we figure out that mobile constellation of devices, and can we launch sort of a collaborative multi-user XR environment? And so we had a bunch of work on sort of different hardware platforms. These are pictures of examples. This was like a beacon that used GPS outside of buildings, and it had a UWB radio. It had this SX1280, which is kind of a narrowband time of flight radio system. We built this sort of mobile unit that you could stick on a phone or a headset to actually track, again, with ultra wideband and a bunch of sort of sensors on board. We moved towards an even lighter weight version that was really a Raspberry Pi, an ultra wideband radio, and then an Intel T265 tracking sensor. We now have a version, since Intel is sadly getting rid of RealSense, we have a version where we're using a Pi camera kind of in a body worn package. And you can sort of see the evolution of where some of this stuff, how this moves. So this was kind of the fixed infrastructure version. So we had fixed infrastructure at the edge of a table, and we've got some students that are walking around. They have phones, they have UWB tags. So they're getting ranges to that infrastructure periodically, and they're being tracked. And you can see that we actually do a pretty good job of tracking them in 3D. Some of my students are engineers kind of walking up the stairs, and it's cool. You can see the spiral staircase track in real time. And we thought, you know, this is great for some applications like law enforcement, where these could be on the side of a car, moving up to a scene or something, but there's really no way that we're going to be able to put those things everywhere in the indoor world. So then we said, okay, well, let's look at sort of the middle of that spectrum. Can we actually do the mapping process? So here's an example of an Android app where you're walking around in a space. It's doing, whoops, I guess I can't. Some videos I can pause with space, some I can't. Interesting. So I'll keep my hand on the pause button here. So this is an Android phone moving around a space. And in this environment, you can see a couple of these ultra wideband beacons that are just at fixed locations. And so this person's just kind of walking through the space unconstrained. There's a bunch of these beacons all over the place. And what we're doing is an online range-only SLAM system that then tries to compute where those beacons are and then overlays their position in augmented reality. So you can kind of get a sense for the error there. It's around 20 centimeters or so, which is what you'd expect from UWB. But it's a very effective way to just very quickly bootstrap this infrastructure. So these devices don't know where they are in absolute space, but they have that relative constellation with respect to each other. And for those that are interested under a hood, this is using a particle filter, and we've got papers on it, and I'm happy to send links about how this works. This is actually all open source and on GitHub, so you can actually run this demo completely yourself. if you want to. So then we said, okay, well, that's great, but can we go one step further and can we do completely relative localization? And one interesting application there is the fact that you could actually have participants in the system that don't even see each other. They can be completely non-overlapping. So you could have a clique of people on one side of a barrier in one part of a building where they can basically exchange their trajectories and ranges to each other to actually localize themselves, but not have to share any mapping information, not to have to see any common overlapping features. And so you can imagine, for example, with Army IVAS, this would be an extremely important capability. And what it boils down to is, you know the orientation of the device. You want to be able to place other users in it. You've got some of these different VIO traces that may be drifting over time. And you want to basically be able to use ranges to apply relative corrections. So this is kind of the classical network localization problem, but now actually sort of extended in 6 degrees of freedom, where you have to worry about doing it real time with real systems. And this is sort of an example of what the algorithm looks like algorithmically. You can see these are all basically particle estimates of the location of users as they exchange messages and move. You can sort of eventually tune in on the actual path that they're taking and kind of figure out their 6 degree of freedom pose. And so it looks okay in MATLAB land. It looks a lot cooler in real life. So here's kind of an example of that system running cross-platform. This is filmed through an iPad that can basically show you, without any infrastructure, the ability to basically bootstrap and get wide area localization running. So this is sort of somebody walking with a HoloLens, again, talking to an iPad, and these all have UWB receivers on them. That's kind of part of the magic. And here's, again, kind of a team of people moving around. And so this is kind of where we are in terms of the relative localization capability. I can show one other quick hint from Chris Harrison's group. He's been working on something called light anchors, which is basically using visible light that's detectable from cameras to actually create very quick anchors with a little bit of data for if you wanted like a URL or a hyperlink into a virtual reality world. It might look something like this. And so, LEDs are everywhere. They're easy to modulate, and we can create sort of the ability to quickly bootstrap local tracking systems that have much more range and can actually do secure handshakes to establish connection. So it becomes much harder to spoof than something like an April tag. So the last bit that I want to talk about is really what's been going on in terms of reality capture and scene understanding. And I think one kind of fun example of this was ISMAR, which is a conference on mixed reality systems. They had a competition for who could create the best virtual hybrid experience. And so the Arena team said, hey, we can do that. We've already been doing that for ourselves. So this is a 3D scan of my lab. And I'd actually encourage you, I believe the website is always live. The components that are running in my lab are not going to be live because that would be really creepy, as you'll see if it was. But anybody who's got a browser, feel free to go to this address, and you can actually use WASD to like move through the space and see the lab. But it's a 3D scan of the lab. We had a couple of interesting features. We had like a 2-directional portal. So a portal with a camera and a screen facing in both directions back to back, where if you're in the real world, you would look and see the VR world registered. If you're in the VR world, you could look through the portal in VR and see the real world projected behind it with spatial audio. So you can actually talk interactively back and forth across the channel. We play some tricks to actually help improve latency and all those good things. Screen share, we had a couple of live cameras that were in the VR space to help connect people in. And we've got this video that sort of shows some of the capabilities and components. So you start off by doing a 3D scan of your space. So this is sorry. Oh, that's too bad. I was hoping I could get away with using the space bar there. So we start off by taking a 3D scan of a space. This is a BLK 360. It's like a terrestrial LiDAR system. Once you scan it, you get that model, which hopefully you guys saw. I know it flashed by very quickly, but you get a model of the 3D space, which you can upload into the Arena. This is now somebody who's going through the space from a laptop in VR. This is an AR person that's going through the space that can see that VR person with audio and video in the space. This is a AR headset where we put selfie cam, so you can actually project the image of the person. And of course, I had the honor of wearing said headset and giving a fake lecture on Rodin. But you can basically see, this is a mashup where some people are real, some people are virtual. If you're wearing the AR headset, you can see basically people in the physical space with the shared screen experience. Here's a quick example of that portal that we were talking about. So, I'm driving through a web browser. I'm coming up and talking to Nuno Pereira, one of the lead developers on the project. And you can kind of communicate back and forth between that portal. I also managed to get a little bit of a snapshot from the ISMAR day with Ivan, who's going through the space, and you can see he's walking with just a mobile phone, right? So I don't know if you caught that. So the phone's rear-facing camera is projecting his head. The screen on the left, this is showing us a video of the VR backdrop. And so he's got his phone, which is putting him in VR. So VR people would see him as that floating head, and he's kind of able to move through the space. I think you could see another VR person just around the back. And you go to the other side, again, you see that reflection. So people in VR are seeing the real world. People in the real world are seeing the VR people. So it's really, because we can very easily combine all of these components together, makes that really, really easy to do. We've extended this. So Chris Harrison has this great project called EduSense, where they're looking at applying this into the classroom to understand attention and gaze. Actually, Ramesh's group at USC is extending this with some of my students to LiDAR-based systems, where I think in this demo, they have a bunch of LiDARs that are outside at USC that are doing live capture of the environment, where they're running analytics. So they're doing like pedestrian detection, bike detection, car detection, and overlaying both the LiDAR stream as well as the analyzed version in real time piped into the arena. So you really get the sense of like the virtual and the physical colliding together. So sort of in summary, mostly I wanted to promote some of the good work that's been going on around the Arena platform. Please feel free to check it out. You can actually drop in with either a private account or a Gmail account, go into rooms and try teleconferencing with it. We also have a bunch of documentation about if you actually wanted to write your own Arena programs that would run on top of it, or just generally if you'd like to collaborate with us on connecting other research that you're doing with these mixed reality environments. A big shout out to the team. So these guys have been amazing. They've been doing a lot of really serious development work and making this thing stable enough that we've actually run multiple events within SRC and within the universities for things like poster sessions or capstone design classes and all that type of stuff, scaling up to 80, 100 users in a single space with audio, video, just working extremely well. It's all open source and available, so definitely worth checking out. And I also want to, of course, thank all of the other PIs across the different universities for their components. I feel like I should have added their affiliations here, but probably some of these folks, but it's just been a huge pleasure to work with such an awesome team. And just on cue, my train is coming by. So with that, I'd be happy to take any questions.
Thanks, Anthony. This is amazing work. Questions for the speaker?
And I apologize if this train gets loud. It sounds like it's a mild one. It's just good.
Hi, Anthony. Really fascinating stuff, really inspiring. I just had a quick high-level question to start with, I guess, about the nature of AR devices. When I imagine exploring the spatial web, I'm in a certain realm and I'm looking for these different scenes. I imagine that might be much more natural or feel easier on a device with a wider field of view, like AR glasses. Do you think that's necessarily an issue for smartphone-based AR, or do you think the spatial web will really reach its full potential when smart glasses become more common?
I think so I don't know the answer to that question because it's a little bit of predicting the future, but I think most people assume that the mobile platform workflow and development that we're seeing right now is just laying the foundation for the programming and the abstractions to move to glasses. Mm-hmm. I find it hard to believe that the end of mixed reality is trapped in a small black mirror that you're carrying in your pocket all the time. but headsets are still a fair ways off. I saw some pretty inspiring stuff at AWE this last week that shows, hey, look, these are steps in the right direction. But a lot of people who've done field testing, even with HoloLens 2, for example, say that, look, for prolonged use, we're still not quite there yet. And they actually like the ability to go back and forth. They like the ability to go from a headset to a tablet if they want to do a quick check. A great example is I saw a nice demo from Boeing about airplane wiring. And their wiring harnesses in planes are insanely complicated. Being able to trace through those with just a mixed reality headset or popping up a phone and seeing it goes a long way. So I do think that we're going to move towards glasses. It's going to take a bit of time. We're not quite there. There's nothing that's really comfortable enough, high resolution enough, low enough motion to photon latency to not make you sick. And this is where a lot of work can come from the EE community, right? Like actually making low power CPUs at the edge that can do this type of processing faster, making better display technologies that deal with divergence and accommodation problems, higher resolution displays, lower power, visible outdoors. Like these are all still pressing challenges that each has their own sort of subdivision and community that's working on.
Great. Yeah, no, thank you. Yeah, I think that's one of the real strengths of this work is the cross-platform, cross-device, because there might be different devices that people want to use for different tasks. And yeah, I think that's going to be really, really useful. Thank you.
Yeah. Thanks. Cool. And I realize people probably have to drop off now since I hit the hour, but.
I have a sort of meta question. So a lot of the work that you're presenting, this is really, really inspiring, really cool. So it feels like it's touching on the augmented reality, but it's really computer systems. So how are you finding being able to convey that work to, let's say, ISMAR community? Has that been, how does that work overall? How do you go and explain to them
that is a great question. I was worried when you said a meta question because that's now a loaded that's now a loaded word. Actually, bridging that gap between communities has been interesting and challenging. So this was the first year that we really actually submitted to ISMAR. We sent in a paper on the arena architecture. It got nominated for best paper. It did not win. So good, but not great, obviously. But I think they're quite receptive. Like I think, we got some really interesting feedback from them. We sent another paper on some of the optical relocalization work where you could clearly see, okay, these guys have been working on this for quite some time. It's not quite as different as coming in from the systems perspective, but I think we're getting there. I think now because the community is probably able to see some of the interface work that they've done come to life. I think they spent a lot of effort on sort of tracking systems that are now also becoming more commoditized. So I think the next wave of challenges they're going to see are going to be the computer systems, platform, edge networking, operating systems, resource management issues. And they know that. They know that this is where there are other fields that have expertise that they should in fact be leaning on and not trying to invent this stuff themselves. Security, right? That has a long, long history. And part of what I like to see about spatial web and the spatial web effort is the web has done, for better or for worse, well, I'd say it's done a reasonable job of security, right? It is the worst possible attack plane in terms of a secure system. I still feel pretty comfortable booking airline tickets and doing online banking. So, that type of knowledge base really needs to trickle down into mixed reality systems. But they've been receptive. They've been receptive for sure.
That's great. Thank you. So we are past the hour. So does anyone have the last question here?
And I think I'm talking with a group of you guys later as well. So.
Right. Okay, excellent. Well, thanks, Anthony, again for such an inspiring talk, and we will have the video as well to refer to for the future.
Awesome. So, yeah, I appreciate it. Thanks again for the invitation.
Right. Thanks so much. And I guess, is Matt still here to stop the recording?
I can actually stop it.
I got it.
Say.
Okay, excellent. Then